we would like to present our work on autonomous exploration. Our approach computes paths that can be followed by an autonomous vehicle to build a complete map of the environment. The approach has been tested on various types of vehicles and in several different environment settings. The exploration problem is still a difficult problem to solve. First, it needs an efficient representation of the environment. As the vehicle explores, we constantly update the representation to keep track of the covered and uncovered areas. Second, it needs to efficiently search the representation for the paths. The existing approaches we have seen are not quite efficient in either task. Many of them are based on greedy strategies. Instead of optimizing the full path, they optimize the marginal coverage for a few steps ahead. Because of that, the exploration routes can be redundant. Back and forth motion is common. In addition, the representation often takes excessive time to update. The vehicle can stop in the middle of a run to wait for the paths. Our approach starts with a fundamentally optimized, hierarchical representation that involves two levels of processing. The local level here is the region close to the vehicle where dense data is kept. The global level spans the rest of the environment where data is kept sparsely in the distant subspaces. The approach optimizes the paths at both levels by solving traveling salesman problems and then joins the paths together. The insight here is that the local level uses detailed processing to make sure the complete coverage in the surroundings of the vehicle. And the global level instead uses a low-resolution representation to generate a comprehensive route which guides the exploration at a high level. The global level trades off the data density for computational efficiency. This approach produces significantly higher efficiency and more complete maps when compared to the existing state-of-the-art. The algorithm runtime is less than half of the existing approaches. The result here is from a lightweight aerial vehicle exploring a section of the university campus. The system integrates a 3D scanning LiDAR, a forward-looking camera, and an IMU for state estimation. The exploration planner takes the registered scan data as the input to compute the paths. What we are seeing now is the overall exploration process at 12 times of real-time speed. The vehicle started from the left side of the scene, explored to the right side, and then returned to the start point in the end. Here, we are seeing the final map built by the system as the vehicle flew. No post-processing is involved. The environment is complex and three-dimensional as we can see. The flight lasted for 5 minutes. The vehicle traveled over 550 meters, and the maximum speed was 2.5 meters per second through the run. This work is currently being used by the CMU OSU team in attending the DARPA Subterranean Challenge. The final event will be held in September this year in Louisville, Kentucky. Our software code is publicly available. In addition to open sourcing the exploration planner, we have released what we call the Autonomous Exploration Development Environment. There are multiple representative simulation environments, basic navigation modules such as collision avoidance, terrain traversability analysis, path following, and a set of visualization tools. This environment is meant to be a platform for benchmarking and also for real robot system integration. Finally, please come to our discussion section to check out our live demos.